Hello everyone, my name is Giorgia Cantisani and I'm a PhD student at Telecom Paris under the supervision of Professors Limessid and Gaël Richard. In this video, we present our method for unsupervised music source separation guided by the listener's selective auditory attention. Specifically, we address the problem of single-channel music source separation, which refers to the task of isolating individual sound sources in the audio recording of a musical piece. State-of-the-art models are generally based on supervised deep learning, where an extensive collection of mixtures and corresponding isolated sources is needed for training. However, despite the release of dedicated datasets, it is still hard for those models to generalize to unseen test data with significant timbral variation compared to training. To mitigate this issue, one can inform the system with additional knowledge about the test data. This approach is referred to as informed audio source separation, and if the additional information comes from another modality than the audio itself, for example the score, the lyrics, or visual cues, as multimodal source separation. In this context, the listener is a rich source of information. Beyond manual annotations, our body reactions to music manifest itself through many observable phenomena. Effects have been observed in the heartbeat variability, in the body movements, as well as in the neural activity. Among those responses to music, we focused on the neural activity characterized by non-invasive electroencephalographic recordings and on the concept of selective auditory attention. The latter refers to the cognitive mechanism that allows humans to focus on a sound source of interest and was studied mainly concerning speech perception in noisy or multi-speaker settings. It was observed that the attended source neural encoding is stronger than the other ones, making it possible to decode which sound source a person is focusing on by observing his brain response. For music, one can recast the problem as decoding the attention to a particular musical instrument. However, it is not straightforward. Unlike the cocktail party problem, where there is one speaker of interest to separate from unrelated background noise, music consists of multiple voices playing together in a coordinated way, making both the decoding and separation problems more difficult. So we propose to use the listener's selective auditory attention as a high-level control to select the desired source to separate and provide priors about it. This guidance is supposed to help the separation process, but also give the listener an interactive and improved listening experience. Therefore, we first studied the problem of EEG-based auditory attention decoding applied to music, and we showed that the EEG tracks musically relevant features highly correlated with the attended source and weakly correlated with the unattended ones. Secondly, we leveraged this contrast to inform an unsupervised source separation model based on a novel non-negative matrix factorization variant we called Contrastive-NMF, which automatically separates the attended instrument. Assuming for now that we have access to the isolated sources, the decoding procedure is usually twofold. First, a feature representation of the attended source is reconstructed from the neural response using a multi-channel binary filter known as backward temporal response function or TRF. Secondly, the reconstruction is correlated with the isolated sources to determine the attended instrument. The correlation scores are generally very low, indicating that the reconstruction is highly deteriorated, but still good enough to discriminate between the sources. So, we have seen that the decoding task is naturally related to audio source separation, as it requires access to the isolated sources to correlate them to the neural data. However, the situation is never met in realistic scenarios such as hearing aids and cochlear implants, where only the mixture of the sound seen recorded by their microphones is available. Typically, in previous studies on neuro-steered speech enhancement, the separation and the decoding task are tackled sequentially. A separation system provides the reference sources for the decoding, and the decoding system selects the source which needs to be enhanced. However, performing the two tasks independently is suboptimal. Within this work, we propose to learn the separation and the decoding jointly. Moreover, to our knowledge, we are the first ones to tackle this problem for musical stimuli. Our model is a variant of non-negative matrix factorization, a technique for unsupervised data decomposition that has been very popular in many audio inverse problems, as it can unmix superimposed spectral components, also in cases where there is no or limited training data. NMF factorizes the mixture spectrogram into two unknown matrices, W and H, such that a divergence on the mixture factorization or reconstruction is minimized. W columns are interpreted as audio spectral patterns, and H rows as their temporal activations. It is also common to impose a sparsity constraint on W and H to improve source modeling. After the decomposition, the separation problem reduces to the assignment of each component to the corresponding source, which can then be recovered through a Wiener filter where the NMF representation is used as a source variance model. However, in real music composition, a source plays several notes with different pitches, and it's hard to represent it with a single component. Moreover, two sources may be represented by similar components as they can be highly correlated. Therefore, it might be very hard to obtain a meaningful factorization in the completely unsupervised scenario, and the component assignment may require specific classification or clustering techniques. To mitigate those issues, the factorization can be guided by incorporating prior information about the sources directly in the optimization cost, for instance, using constraints, regularizers, or pre-trained dictionaries. In the multimodal scenario, where one has access to multiple views of the same phenomenon synchronized with the audio, one can, for instance, impose the equality or the similarity of the time activations in the two modalities. In our case, this is not applicable, as the time activations reconstructed from the EEG are significantly deteriorated, making it hard to use them directly. Nevertheless, we know that these reconstructions are good enough to discriminate the attended instrument from the others, leading to a contrast that can guide the separation. So, we propose a framework where the factorization and the decoding are learned jointly. The target instrument activations are reconstructed from the multi-channel EEG using a pre-trained TRF model. Those activations are then used to guide the mixture factorization and cluster the components into the respective sources, obtaining two submatrices of W and H associated with the attended source. The decoding model is not fixed and is updated every certain number of NMF iterations to adapt to the observed signal, using WA as a new feature extractor. After convergence, the dictionary and the activations related to the attended source are used to obtain the corresponding Wiener filter mask. Looking closer at the contrastive-NMF cost function, we can observe an additional term we called contrast. Thanks to this term, the total cost aims at decomposing the audio spectrogram while maximizing the similarity of the EEG-derived activations with the audio-derived ones for the target source, and minimizing it for the interference sources. In practice, the projections are learned to maximize the discrimination ability of a TRF model. The experiments are designed to evaluate whether the EEG information helps the separation process. However, to verify that the improvement is due to the EEG and not to the cost function discriminative capacity, we built a second baseline, which consists of the contrastive NMF to which meaningless side information is given. In the two baselines, the components are clustered according to their MFCC similarity, while the EEG-informed model automatically identifies and gathers the target instrument components. For this work, we used the MED-EEG dataset, a collection of 20-channel EEG signals recorded from 8 subjects while listening to music and attending to a particular instrument. The quality of the separation is then evaluated in terms of signal-to-distortion ratio expressed in decibel. In the figure, one can compare the SDR results for different methods and instruments in the dataset. Our model performs significantly better than the baselines for all the instruments except for the bass. Nevertheless, also for the bass, the EEG-guided model automatically clusters the components and identifies the target source, which is already an asset with respect to the baselines. The high variance experience when separating the bass and the drums is due to the high variance experience across different subjects, for whom the attention task may be more or less difficult. In figure, we can see the SDR results for the EEG-informed model only across different subjects and instruments. The intersubject variability is particularly evident for instruments like the bass and the drums, which are notably more difficult to be tracked, especially for non-professional musicians. Singing voice and guitar work better in this sense. However, we have to consider that the voice is a particular instrument for which the attention task is radically different from the other ones, as it also involves semantic cues. Moreover, all subjects involved in the experiment, except for two, play guitar as a hobby and are particularly trained in following this instrument. The proposed approach is for single-channel source separation. Nevertheless, the stimuli were played to the subjects with two possible spatial renderings. One where both instruments are in the center, denoted as monomodality, and one where the instruments are spatialized, denoted as stereo. This experimental setting allowed us to study if the spatialization helps the attention task, with consequent benefits for the separation. In the table, we see the SDR results for these two different cases. Our hypothesis seems to be verified for guitar, singing voice, and drums, while the bass performances confirm that it is the most challenging instrument to be spatially localized by humans due to the low pitch content of its signals, which add ambiguities and makes the attention task more difficult. On the contrary, the drums, whose signals are mostly impulsive and thus easier to localize for humans, are the instruments for which the stereo listening helps the most the attention task. So, to conclude, our results support the thesis that the EEG can guide and help a source separation system, especially in difficult cases where non-informed models struggle. Our ablation study, where the proposed model is informed with random side information, shows that the proposed model is not enough by itself but needs to be informed with meaningful side information, and that the activations reconstructed from the EEG are indeed meaningful. The main advantage of the proposed approach is that it allows reformulating the attention decoding problem without the need for the ground truth sources, which are not available in real applications. However, we need to keep in mind that any EEG-driven system has the intrinsic limitation of the subject variability. If the level of attention of the subject is not sufficient, this will impact the performance. So thank you very much for your interest in our work. Online you will find additional material, such as audio examples, the detailed derivation of the CNMF update rule, and its Python implementation.